Welcome to the first video in the second block of the course that is about differential geometry. Now, why do we need differential geometry? Well, here's the thing. First of all, let's understand a little bit better what is differential geometry. Let me give you a definition, quote-unquote definition. This is just me, don't blame anybody for this. Now, how am I supposed to do vector calculus? I mean, I know how to do vector calculus in Rn, right? But how am I supposed to do vector calculus with a freaking bag of potatoes? Or with friendship? Oh, here's friendship. Do vector calculus with it. And you would be like, what the? What are you talking about? You see, differential geometry, let me make an edu definition, so my own definition. Differential geometry is the art of doing vector calculus with things that you never think that you could do, that you would never think you could do vector calculus with. All right, and why do we even need that? This is a pretty abstract branch of math, an amazing and a super cool branch of math that when you actually understand, you start understanding everything else and everything clicks. Sure. Why do we need that? Well, we need that because we're gonna have to do calculus with something that is not Rn. It's space-time. And space-time is something that, even though many people think of it as something like R4, as in like, yeah, time is another dimension and so on, it's nothing like, well, I mean, it's not R4. Locally it may look a bit like R4, but it's not R4. So we need to learn how to do vector calculus in things that are, with stuff that is more general than just Rn. And that is what we're going to do by learning differential geometry, or at least, again, don't take this as a course on differential geometry. There's an intro, a preparation to be able to use at user level differential geometry. But we're gonna try to understand everything, all the structures that we can build to be able to do vector calculus with friendship or a bag of potatoes, and at what point, so what does it mean to have curvature? What does it mean to have, what's a vector even in those cases? What is a vector? You know, we're going to have to generalize the notions that you knew from calculus or from analysis. We're going to have to generalize them. And that generalization will bring us a lot of joy. And I promise it will, because we will see exactly how many things and how many levels we need to build to have all the structures that we need. For example, I don't know, having a metric, oh, that comes very late. The notion of curvature does not require a metric. We will see all this, and hopefully we will learn along the way a little bit of this abstract and amazing branch of mathematics, at least at a level that we are able to use it to describe space-time. All right, so let's begin. All right, so let's start by talking a little bit, what do you mean by bag of potatoes or friendship? What are you talking about? Let's start by introducing the notions that will allow us to understand what I mean by giving the ability of doing a vector calculus or analysis to a bag of potatoes. Let's begin with the notion of topological space. So what is a topological space? An easy notion, I hope. It's a set of points, right? It's a set. I call every element of the set points, together with a set of neighborhoods, like ways of making groups of those points. Now, more specifically, I want a set, X is a set, and then I call S a collection of subsets of X, right? And that collection of subsets, I demand that three axioms need to be satisfied. The empty set and the whole set have to be part of this collection of subsets. Any arbitrary union of elements of S belongs to S as well, and any finite intersection of elements of S belongs to S as well. The difference here is finite intersection versus even infinite union. An infinite unions of elements of S have to be within S, whereas only finite intersections need to be within S. All right, so you know what we call the elements of the set S? So the elements of subsets of X that satisfy the three things have a name. Do you know what that name is? I know some of you do. The name is open sets. No, really, we do call them open sets. So the elements of S, the collection of subset of X that satisfy these three axioms, we call them the open sets. And with this, we call this defining a topology on the set X. That's it. And it's kind of interesting because these open sets give a notion of neighborhood, as I said here, because it's like, you know, a notion of what connects with what. What is in the same subset as what. I'm gonna give you a couple of examples, very easy examples, and then we talk about more difficult examples, like how do I mean by friendship being something like this. Let's see. So to understand the notion, let's give several examples. For example, this one. All right, I have a set of 3 points here. So I call the set X the set that contains A, B, and C, just 3 points. Okay? A, B, and C could be, I don't know, could be tables in my room. I can give a topology to the number of chairs in my room, or the number of tables in my room, or the number of pens that I have. You can think that, how about that? Let's do it with pens. Right, so I have now a set of 3 pens. I call them A, B, and C, so as in black, blue, and red. Okay? And can you give a topology? This is a set. Can I give a topology, make it a topological space? I can. And I can do it in many different ways. We're gonna do it in several different ways here. So, yeah, you ready? You see how the potatoes come? These are like pens, markers, right? I'm gonna give the set of these 3 markers topologies. Let's see. So the first topology I'm gonna give it is what we call the trivial topology. So I'm gonna, the set X is the set of the 3 pens. I need to define the collection of subsets that satisfy these 3 things. Let me give you one. First of all, the whole set will be 1. So the whole set will be one element of S. Let's call it maybe S1, okay? And the empty set needs to be part of it as well. So the empty set, I call it S2. So I have the set X, this is the whole set, X, right? The set X, I made it a topology by defining the set S1, which is the whole set. S1 equals X, and S2 equals the empty set. All right, so I have 2 subsets of X in the collection, and let's see if it satisfies the 3 actions. The empty set and the whole set belong to S. Definitely, they do. Empty set is S2, the whole set is S1. Wonderful. Any arbitrary union of elements of S belongs to S. Let's see. There are 2 elements only, so the arbitrary union that I can have is the total set with the empty set, which is the total set which belongs to S. Wonderful, we'll satisfy the second. Any finite intersections of elements of S belong to S. Yeah, sure. We can have the intersection. What is the intersection between the whole set and the empty set? The empty set. Nice. That intersection is the empty set, so it's within S. It's S2. Wonderful. So this is a topology. The pens, the black pen, the blue pen, and the red pen, together with the collections of subsets of the pens, which are the whole set and nothing, well, the empty set instead of nothing, is a topology. Wonderful. In this case, there's only one neighborhood. The 3 pens are equally in the same neighborhood. We'll talk. There's a notion of closeness, but not a notion of quantifiable closeness in terms of the meters and distance, right? We will talk a little bit about what is the notion of closeness that I define when I define a topology. Basically, what I'm saying here is that the 3 pens, the 3 markers, are equally close to each other. All right, wonderful. But this topology is pretty trivial. Let's do another one. How about this other one? Right, I added an extra set. I'm gonna call it S3, an extra subset, right? And that subset is, so S3 is just the element A, which means the black marker. All right, now question, is this a topology? Now it's different, right? The set S now has, the collection S, if you want, is a set of sets, has 3 subsets of X. Has the whole set, the empty set, and then the element A. All right, so let's see if this is a topology. The empty set belongs to S. That's true, that's S2. The whole set belongs to S. Yeah, that's S1. Okay, cool. That is satisfied. Second, any arbitrary union of elements belongs to S. Well, let's see. The union of A with the empty set is A. That is definitely here. It's S3. Wonderful. The union of A with the whole set, oh, that's just the whole set. So, wonderful. That is certainly in S as well, because it's here. What about the union of, I don't know, the empty set and X? Well, certainly, same as before. It's definitely here because it's the whole set. What about the intersection? Well, let's see. Intersection of A with the empty sets is the empty set. So it is here. Wonderful. We're fine. Intersection of A with the whole set. That is A. All right, it is here. Wonderful. Intersection of the total set with the empty set. That's the empty set, which is here as well. Wonderful. We're fine. This is a topology as well. There you go. A different topology. So we had for now, let's just write S with no problem, I don't know what to call it, S Roman 1, just to do something, being. Right, so this thing is just S1 and S2, right? So the set X with the topology S1 forms a topological space. Wonderful. Same happens with S2. S Roman 2 is S1, S2, S3, right? Well, certainly X with S2 is also a topological space. Less trivial than before. Now you say that there's something special about A, and then there's this two. There's A, and then there's this two. We will talk a little bit about that notion. But you see, the open sets kind of distinguish things that are, it feels to me that A has something going on, and there's something further away, B and C, that are here at the same level, but farther from it in a way. The notion of farther, remember, is not associated to a metric or a distance. It's associated to something else, with the notion of neighborhood. There's a neighborhood that only contains the black one, and there's a bigger neighborhood that contains the three of them. So the black one is kind of special, has its own neighborhood. All right, let's try another topology. Can we give it another topology? Sure, let's do it. All right, there is something here, but is this a topology? Maybe I'll call S4. This is I add another set, S4, that I'm gonna write here. S4 is B. Is this a topology? Actually not. How do I know? Well, because any arbitrary union of elements of S should be an element of S. And if I do, for example, the union of S3 and S4, what is that? Well, that is a set that would be this one. Oops. That set would contain, let's call this one S5, and this S5 is not within the topology that I defined with the collection S, but I can add it though, if I add it. So if you wanted an example of not a topology, just don't count S5. I should have curly brackets here if you want, because I'm abusing a little bit, but I think you understood. S5 would be the union S3 union S4. All right, so wonderful. So if I have that, is this a topology? Well, yes, because with S1, S2, S3, it was a topology. We already checked. If we add these two, we say that we added the union of S3 and S4, which is the only thing that broke it before. So this is certainly a topology. Wonderful. Can we, so you see there's something going on here, interesting, between, it looks like the black marker and the blue marker, even though they're special, they have their own neighborhoods, but also they share something that the red one doesn't. The red one is kind of further away. I dropped the marker. Right. So the red one, it's further away from these two. They have their own thing. You know, the black one has its own thing, the blue one has its own thing, and also they kind of are close in a way, but then the red one is left apart. So it's kind of further from them, right? Okay. How about we make one more? So by the way, of course, we can define S3 as S1, S2, S3, S4, S5. And of course, this would be also a topological space. All right, so let's do one more example, and then we move on and talk a little bit about how this applies to friendship, for example. Okay, so we have here another possibility of definition of a topology. Let's see. I have the black, the blue, and the red. And the black, the blue, and the red, I define, of course, the subsets. Here, S1 is the whole set, S2 is the empty set, S3 is A and B, S4 is B and C. Now, is this a topology? No. And what fails? This one. Because if we compute the intersection, what about the intersection of S3 intersection with S4? What is that? Well, we know that that's B. And there is no set that contains only B in here. Fine, let's fix it. S5 equals that. So let me have another subset here, S5, right? That makes it a topology. And then indeed now, this set, well, you can call it S4, but it's different ones, right? But it's a collection of 5 if you want the same way. This is a topology, okay? And this is a topological space now. All right, wonderful. So let's go back to an example more like the previous one, and let's talk about a way to understand what do I mean by potatoes or friendship and notion of distance and so on. So how does the definition of a topology allows you to establish a notion of closeness? So I don't want to say distance because distance feels like I'm measuring, which is nothing like this, like a notion of closeness. Well, let's think about friendship, which is just an example that I gave. In friendship, there's a notion of closeness, how close a friend is. And you say, okay, I have the group, the set of my closest friends, and then there are other sets, right, that contains those friends as well, and maybe other people, which is the friends that I go out with, in the sense, okay, I have the closest friends with whom I actually share all my secrets, and then I have the friends that I go out with. And of course, I also go out with my best friends, right? So, you know, this notion, you can tell, okay, how many people are there in the second set, in the set, how many people are there in the set of people that I go out with? 1, 2, 3, 4, 5, 6, 7. Okay, 7. And how many people are there in the subset of close friends? 1, 2, 3, maybe 2 or 3. Okay, cool. So then if you can count the number of people in the smallest set that contains them, and that tells you how strong the friend is. For example, a friend that you go out with but don't share secret, the smallest set would be the set of all the friends you go out with, which is 7. A friend that you go out with but also you confide to, that would be in the set of 3 people, the smallest set of people. So you see the number 7, number 3, in a way give a notion of closer in a neighborhood, you know? So the notion of friendship is very similar and amenable to the notion of, well, a way of defining open sets in a set. For example, here I have Alice, Bob, Charles, and Voldemort. And you see, Alice is very in touch. It could represent Alice is really in touch with herself. She's her best friend in a way and takes care of herself, healthy feelings. Takes care of her mental health, which is a very important thing to take care of. And then you have Bob, kind of a best friend, and you know, you put them together because they share a really close bond, they share secrets. And then there's Charles. Charles, Alice and Bob, they go out together. But of course, Bob is, you know, confiding with Alice. This is the set of people that Alice confides with herself and with Bob. And this is the set of people as 5 that Alice go out with, which is Alice, herself, of course, Bob, and Charles. And you can tell, well, there's Voldemort, nobody likes Voldemort. So the thing here is that, you know, you can tell this definition of these subsets of the set of people here, 4 people that I have, defined like that, is a topology on this set of 4 people. And you can tell that there's a notion of closeness. There's the neighborhood. In the immediate neighborhood of Alice, there's Alice. In the a bigger neighborhood, there's Bob. And then in a bigger neighborhood, there's Charles. So there's a notion of closeness, if you know what I mean, by the number of elements in the smallest open set that contains the people you want to check how close they are. All right. So I hope that this clarifies the notion of topological space. Now we have to make it a little bit more complicated because these are finite sets. It's very simple. But space-time is not a finite set. There's an infinite number of points in space-time, right? And of course, a bag of potatoes could be a finite set. But what about an infinite bag of potatoes? So when the topological spaces have infinitely many elements, things can become a little bit more complicated. We need to define another notion before getting to our starting point to start doing differential geometry. Those notions are the following. The notion of topological manifold. Let's call it M. A topological manifold is, first of all, a topological space, which is what we define. Remember, it's a set of points with definitions of open sets that form a topology, satisfy these 3 actions that we talked about. That is Hausdorff, and such that every point possesses an open neighborhood homeomorphic to Rn. Okay, what does that mean? What does Hausdorff mean? Hausdorff means that for every 2 points of the set can be separated into disjoint open sets. So if I have A and B, there are many, imagine A, I don't know, for example, imagine A here and the point B here. Of course, there would be open sets that contain both, like that. But I am saying if it's Hausdorff, for every point, there is an open set or 2 open sets that are disjoints that contain the point. You can separate, in a way, the 2 points into different open sets. So there are such things as local neighborhoods in which you can separate one point and exclude others. I can always exclude other points that is not that one by making my open set smaller. That's what I mean by Hausdorff. All right, what is homeomorphic? Homeomorphic means that there is a bijective continuous map. And it's actually bicontinuous, as in the map and its inverse both are continuous. That's what we say when it's homeomorphic to Rn. That means that it is possible to have a map, to have a homeomorphism that relates open sets around every point, right? We can map them to Rn. That is what it makes an action. So every point of the set, or an open set around every point of the set, at least some open set, maybe not a big one, but maybe a small one, there is at least some map that I can define that will be bijective, and the map and the inverse are both continuous. That's what it means to be homeomorphic to Rn. So I can take neighborhoods in my topological space and map them to neighborhoods in Rn. How do you know if one is well, if I can tell you the maps, then I know it is, and that's what we're gonna do. It's precisely finding maps or ways of mapping in a way that is bijective, bicontinuous, the open sets in the topological space to open sets of Rn, that we know what they are, because you've studied in calculus what an open set in Rn is. Wonderful, right? All right, so how do we do that? Well, let's see. All right, so we have here a topological manifold. The topological manifold, you can think of it as points in space or anything. No. It's like whatever you want, potatoes, infinite potatoes, abstract things. We have no freaking clue how to do calculus in here. We are simple people. We can only do calculus and analysis in Rn. We don't know how to do it in the infinite potato set, whatever this topological manifold is. However, if it's a topological manifold, I know that locally around every point, there must be something that can be made look like Rn. For example, I have the point x. Imagine that this is space-time, for example, right? I have the point x. This point x represents an element of the topological manifold, an element of the manifold. And that element of the manifold is in an open set here that I call U sub A, that contains the point and some points around it, some neighborhood. And because this is a topological manifold, I can find a homeomorphism, let's call it phi A. This homeomorphism has an inverse, and both are continuous, and maps a point in the manifold to a point in Rn. I wrote R3 as an example in this case. This would be if you can do these maps to R3, and R3 is the smallest Rn that you can, the smallest n of R. When I say Rn that you can do this, that would be the dimension of the manifold would be dimension 3. But anyway, let's keep going. So we have the point x of the manifold mapped through this phi to a point phi a of x in R3. And this is nice because what this is doing for me is giving the point coordinates. How? Well, this map gives me a point in Rn and R3, and a point in R3 I can represent by its coordinates with respect to this axis, this coordinate curves that I have here. So I can assign coordinates in a way to a point by mapping them to R3, where I know how to assign coordinates and how to do the useful calculus. So I call x mu here the coordinates of x under the map phi a. Now, this map phi a would actually take any point in this open set UA to R3. So we call a chart, this is the definition of chart, a chart is a pair of an open set and a homeomorphism that maps, of course, elements around a point of an open set, right? Elements of that open set in the manifold to R3. All right. So you see, if we have a chart, we can assign coordinates, at least locally, to every point around x in this case, every point in the open set UA. All right, but maybe there is another, let me write this one here. Maybe there is this guy. Let me call it UB, right? This is a different open set, and you don't go to Rn through phi a. You need to define a different homomorphism to go to R3. Well, let's see how we do that. All right, so now I have here another way of going from the point to Rn. I have now another chart, which is another open set, UB, that also contains x, and another homomorphism that goes from UB to R3. Now, it doesn't have to go to the same points. Think of it as, I kind of drew it in a way that it looks the same point, but I think this one could have been here, for example. Right, so this is a different way of assigning coordinates. I call them the prime coordinates here. I'm mapping to R3 in a different way, and I call this different coordinates. I have different coordinate curves here, right? So there are two different ways here of assigning coordinates to the point in the manifold x. by mapping it to Rn through the chart UA phi A, I get the coordinates x1, x2, x3, and mapping it to R3 through the chart UB phi B, I actually get a different set of coordinates x1 prime, x prime 1, x prime 2, x prime 3. So you see, there are many different ways in which we can do, we can associate coordinates, we can construct local coordinates in open sets of M. Now, if we really want to do something that works, I want this to be able, right? You can think of it in a way from like when you assign to some set of points, you assign like, oh, I'm going to represent this with spherical coordinates, I'm going to represent this with Cartesian coordinates, right? There are different ways of finding maps that assign coordinates to points of a manifold here. Now, they better work together. You better be able to go from one assignment of coordinates to another, right? Some intermediate, some transition map, right? Something like that. What would that look like? Let's see. So I desire a map that can take me from R3 to R3, that takes me from the coordinates without primes to the coordinates with primes, right? It's a map from R3 to R3. If you want, you can think of it as different open sets in R3, or you can think as two independent copies as I drew here. Either way, in the notes, for example, I have it with the same copy if you want of R3 and two different regions. But I do want a transition map, something that takes me from R3 to R3 in a way that associates the coordinates that I assign through phi A to the coordinates that I assign through phi B. But what map is this? Well, I want it to go from here, from this R3 to this R3. How do I define it? Well, I know how. I can go, so I don't know how to go directly. I have no idea, but I can go indirectly. I can go from here back to the manifold, and from the manifold here. I can do that. So I first go from R3 to the manifold through phi A minus 1. I go this way. I end up here, and then I apply phi B, and I end up here. So the composition, this symbol represents composition of maps, right? If you want, I can write it equivalently as phi B of phi A minus 1 of x mu, right? I apply phi A minus 1 to x mu, that takes me to x serifa, the proper point of the manifold, no, its representation in some coordinates. And then from there, I take phi B, and that takes me to x mu prime. All right, to be exact, to be accurate on this, I would have had to apply this map to x mu, right? To have it accurate, because this is the map, and this is the map applied to the point x mu, what I wrote here. But you get the idea, right? How that works. So this map, phi B composed with phi A minus 1, takes you from R3 to R3 through this path, going through the manifold. So this is a map from R3, a true map from R3 to R3. And that is nice, because maps that do things with the manifold, I don't know how to do things with it, but maps that go from R3 to R3, Rn to Rn, oh, I know those. That's vector calculus, right? Functions that go from R3 to R3. Interesting. So I know how to handle those. Let me just write this properly. And now I can say, well, are these functions, I can talk about smoothness of these functions. Are these functions continuous, have derivatives? I know how to take derivatives now, because I know how to do a derivative with respect to a function that goes from R3 to R3. That's what you studied in vector calculus. Wonderful. So I can talk about the smoothness of that function. That's a fun. These things, I can't talk about smoothness. All that I need is that they're by continuous invertible and continuity in the set of open sets, right? If I move from one point to another to the open set, I don't get jumps in Rn. The continuity is defined through, it's not mapping this continuously in Rn. I can talk about continuity, but I don't know how to talk about differentiation or derivatives of smoothness. But this one, the transition map, I can. So that allows me to define the notion of atlas like follows. We define here an infinitely differentiable atlas, or a smooth atlas, as a set of charts, which, remember, is a set of open sets and the homomorphisms that go with those sets to map them into Rn, covering the whole manifold. So I want as many as to patch the whole manifold, and such that the transition functions like this, one, right, mapping Rn to Rn are smooth, are class infinity. That is what we call an atlas. It makes sense, right? Charts that map regions, small regions to Rn. Atlas, it maps the whole manifold to Rn through many charts, right? So we call, now that we have this notion of infinitely differentiable atlas, class infinity, some of you may have not seen that. Class infinity means that it's infinitely differentiable. Class infinity means that it's infinitely differentiable. Okay, you can differentiate it infinitely many times, and it's of course very smooth. And class infinity, or smoothness, or having infinitely many derivatives makes sense because those are functions from Rn to Rn, which is where we know how to do calculus. You see how structures start to appear? Now we can apply things that we know for calculus when we have those functions. I mean, you see this is the beginning of it. We're trying to translate in a way the manifold into things that we know how to calculate on. All right, now if we have a topological manifold, let me call it topo manifold. Fun fact, you know what topo means in Spanish? It's mole, the animal. Anyway, whatever. That's why I find it slightly funny. A topological manifold plus an infinitely, well, let me just call it smooth because it's shorter. Smooth
atlas gives you what we call
a differentiable manifold. Differentiable manifold. And the structure of differentiable manifold is what we study in differential geometry and what we used to build all the calculus now. Try to say, okay, now that we have that, can we talk about vectors here? Can we talk about functions? Can we talk about vectors? How about tensors? This kind of thing. In your bag of infinite potatoes, in your infinite potato bag, you have a way now, perhaps, to define vectors, to define tensors, to define structures the same way that you can define it in Rn. One exercise I can leave for you is argue why, for example, for Rn, you only need, for an infinitely differentiable atlas, you only need one chart, that's enough. And argue why on a sphere, you need at least two. If your manifold is a sphere, and you want to give the sphere structure of differentiable manifold, you need at least two charts. Okay? Think about it and we can discuss it in the live sessions. All right, so today we've done several things. We had introduced the notion of topology and topological space. Then we talked about topological manifolds, and now we've seen how to give topological manifolds structure of differentiable manifold. This is the end of this video for now, but I'll see you in the next one. Until then, take care.